Chem 4 type topics here. So as we finished in lecture earlier, we did finish the electrochemistry chapter, so that's all wrapped up. And again, our exam will be today's Wednesday, so 1 week from today on the thermodynamics chapter and also the electrochemistry chapter. And honestly, that kind of doesn't leave us much left to go here. So it's going to be like, I think, this chapter and maybe some kinetics. And then that's all she wrote, I think, for chapters for out of material at that point. All right. So again, these lecture notes are obviously up there where all the other lecture notes are up there. And we're just going to kind of get a little bit into it here. And then, that'll hopefully kind of keep us on some pace here. All right. So in this chapter, we're going to talk about transition metals first off, and some of it may be a little bit of a review for you about some of the properties of transition metals and so forth. And then we'll get into coordination compounds and sort of coordination chemistry. And the reason we sort of talk about transition metals a little bit here up front is a lot of coordinated sort of complex ions and stuff like that does involve or do involve transition metals. So it's good to, again, remind ourselves of some of the properties of transition metals because they do pop up a lot here in this type of chemistry. So first couple of things we're going to talk about is, for example, effective nuclear charge. And effective nuclear charge is sometimes referred to as Z effective. And you might be familiar with this from last semester, but just in case you're not, what effective nuclear charge is really sort of the charge that really the positive charge that an electron sort of feels. So the kind of attractive force to that positive charge that it feels sort of in an atom. And it is sometimes different, sort of the charge that is felt by an electron, depending on sort of where the electron is located in an atom. When we talk about electrons, for example, if we looked at, say, lithium, for example, lithium has 3 total electrons, electron configuration, 1s2, 2s1, right? There's kind of 2 types of electrons. These guys here, which are closer to the nucleus, they're sometimes referred to as core electrons. These guys here, which we're oftentimes familiar with, these are the ones that are highest in energy, a little further away from the electron. These are our valence electrons, right? And those obviously valence electrons are the ones that are involved in bonding. And obviously when you draw Lewis structures and all those type of things. So when we have these different sort of types of electrons, really our core electrons and our valence electrons, although they're in the same atom, they are sort of feeling a difference in sort of the attractive force between the nucleus and those electrons. Also a reminder here, hopefully you know this, but in the nucleus, right, we have our protons, which are positively charged. Also our neutrons are in there as well. Our electrons are out from a distance, right, traveling around. But because electrons are negatively charged, because protons obviously are positively charged and the nucleus is positively charged, basically, there's an attractive force right between those two guys, kind of the electrostatic attraction that occurs. So when we look at, say, something like lithium, right, it's got like a +3 charge sort of happening there in its nucleus because of the 3 protons that are present, and obviously some neutrons which have no charge, which are not really playing too much of an effect. We got kind of those core electrons closer to the nucleus there, and then kind of behind those core electrons, a little higher in energy, a little bit further away, right, we have our sort of valence electron, right? So what is sort of the difference in terms of the charge that is felt by, say, our core electrons here versus, say, our valence electrons? Well, in this really badly drawn example here, you could really see that there's really nothing in the way, right, of kind of these core electrons and the nucleus. They're really lower in energy. They're close to it. So really these electrons here, they're feeling really like that full brunt of that sort of +3 charge, right? But When we get to our valence electron, which is sort of behind, if you want to think about it that way, of our core electrons, we get a process known as shielding to occur. And what is shielding? Shielding is basically when lower energy electrons basically shield higher energy electrons from the positive charge of the nucleus. Right? So what does that mean? It's like when you went to the movies and, before they assign seats, I suppose, you could get there early, you get your seat right there, dead center in the movie theater, right? You got a nice view of the screen. And, right before sort of the movie starts, somebody comes in and they got like a giant hat that sits right in front of you. That person just basically shielded a lot of the screen from you. And that's sort of what's happening here with these electrons that are in lower energy level. They're sort of taking the full brunt of that positive charge. And the guy on the outside is not really feeling that full +3 sort of positive charge like we were talking here with lithium. It's feeling sort of an effective nuclear charge, which is our Z effective. And you can kind of calculate it relatively easy. The positive charge, right, is the number of sort of protons there, minus the number of electrons that are shielding, which in this case is 1 and 2, gives us a +1 charge. So that valence electron here in lithium, he's only feeling really a +1 sort of effective charge coming off of that nucleus. Why is that important? Well, a couple of things. One, as you might remember, when you talk about sort of a positive and negative attraction, the force between those things, it increases with the charge size. So something that's like +3 and -3 will be held together a lot stronger than, say, something that's +1 and -1. That also explains why, right, when we talk about bonding and electrons that are able to be sort of involved in bonding, transferred, shared, it is these valence electrons that are doing that because on average, they're really not feeling that full attractive force of that nucleus. That in turn is going to allow them to really be sort of popped off a lot easier, removed a lot easier, shared a lot easier. The general trend in terms of effective nuclear charge is, it typically across a period, it increases. So as we go sort of across a period, the effective nuclear charge typically will increase. And that's what we're looking at here. This is period 3 on the periodic table. So like period 3 here on the periodic table, sodium, magnesium, aluminum, and silicon. And what we see is the effective nuclear charge really does increase as you go kind of left to right there on the periodic table. Now, what does that do in terms of size that's related to these atoms? Well, we can also see the relationship of the radius there, the size of atom as we go across a period on the periodic table. It gets smaller. And that also makes sense if you think about the effective nuclear charge. Somebody like sodium's valence electron is only feeling a +1 charge. Somebody in silicon's sort of valence electron is feeling more of a +4 charge. Again, that greater effective nuclear charge as you go to the right is going to bring the outside electrons, even though they're further away, in even closer. So the overall sort of size of the atom ends tends to shrink as a result of that. And that's what we see here if we sort of look at it. Again, we're sort of building up protons as we kind of go this way on the periodic table. Building up those protons are going to essentially result in a greater sort of positive charge. And again, even those sort of outer electrons are going to feel an effective nuclear charge that's larger and is going to bring them in closer to the nucleus, shrinking sort of the overall size of the atom, as opposed to if you're on this side, exaggeratedly drawn here. Again, those outer electrons aren't going to feel as much of a pull in, and the size of the atom will, basically be a little bit larger as you go to the left there on the periodic table. Any questions on that there?
Professor,
Yeah.
what is the significance of the radius here?
The significance of the radius, it ties in with effective nuclear charge. So as we were just talking about, basically this period on in that last slide in terms of effective nuclear charge, this guy had like a +1, +2, +3, +4, and so forth. So what that means is, again, you have these like outer electrons, right, on all these guys, the valence electrons. So because the effective nuclear charge, even on those outer electrons, is getting larger as you go to the right, what that's going to do is basically pull those electrons in towards the nucleus, and the result of that is the overall size of that atom will actually start to get smaller, because even the furthest away electrons are going to feel a stronger positive charge and going to be brought in closer to the nucleus, resulting in a sort of smaller radius or size for the atom as you go to the right on the periodic table. Again, if you just want to think about it like a sodium here, we'll just do like a 1-to-1 sort of relationship. You know, if we're thinking each of these dots are the valence electron, the outermost sort of electron, right? Because this guy has a +4 charge, it's going to pull even that outer electron in much closer than the sodium guy would be pulled in. The result of that is, you know, if you just kind of draw it like that, you know, we're going to end up with a smaller overall size for that atom. Other questions on that? All right, so this is an important sort of idea again in terms of the size and the trend that we see. But let's talk about really what we're going to talk mostly about is sort of in this chapter, which is transition metals. So a couple of reminders. Again, hopefully you're familiar with where our transition metals are. It is between group 2 and group 3 on the periodic table is our transition metals. So all these guys, you know, within here in this area are transition metals. And a lot of times we talk about the first row transition metals, which are these guys here, and the second row and so forth. So transition metals are here. These guys on the bottom you might also be familiar with are also, technically speaking, transition metals. They're sometimes referred to as inner transition metals. That's because if you look at the numbering, this guy like is 57 in terms of its atomic number. This guy is like 72. So there's a big jump there. And that big jump is actually this guy. This guy should technically go right about there. Same thing if you look over here, this guy is like 89 in terms of its atomic number. This guy is like, I don't know, like 104 or something like that. But if you come down this way, this guy is 90, and this sort of row should technically go right there. Those are, again, sometimes referred to as the inner transition metals, and also known as the lanthanides and actinides, because those are the guys that they technically should follow. In terms of electron configuration, you might also remember that this is your D block. That's your F block. By the way, the first two here are your S block. These are your P block in terms of electron configuration, right? And just a reminder, right, when we talk about electron configuration, which we'll might touch upon it here in just a second, you could put 2 electrons there in the S. P, you could fill up the entire subshell with 6 electrons. D, you could fill it up with 10 electrons. And F, you could fill it up with 14 electrons. And you literally can, if you know what you're doing, that is 1, 2, 3, 4, 5, 6, and 7. The period number is the N number, right? So that is your principal quantum number. And you can actually just count off electron configuration. So S has 2 electrons, so that is 1 and 2. P has a grand total of 6 if you fill up the entire subshell. That's 2, 3, 4, 5, and 6. D has 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. F has 14. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So you literally can sort of count off electron configuration, you know, from the periodic table if you know what you're doing. For example, if we were going to get to our guy that we were just looking at, for example, actually, we'll go a little bit further than him. We'll go like magnesium, which is like right here. If we wanted to get to magnesium's electron configuration from the periodic table, you literally could just sort of count it off. This would be 1s2, 2s2. This would be 2p6. This would be 3s2. So you could literally sort of count it off the periodic table. When I say if you know what you're doing, because hopefully if you do that, you know there's a couple of things that are a little bit different. The transition metals, which is right here, number 21, this is actually 3D. It is 1 behind the period number. This would be 4D, 5D, and 6D. And F is actually 4F here and 5F. And that actually is 2 behind the period number when you get here. So, you know, there are a couple of places where if you're going to do electron configuration, you do want to be careful because, you know, there are some places where it doesn't go in sort of the correct order if you don't know what you're doing. Transition metals show a very great similarity in terms of a given period and also within a group. And also a reminder when we talk about the periodic table, just to hope so periods go this way, groups go this way, right? Just a reminder on that. So obviously things in the same group, for example, you know, like the alkali metals, alkaline earth metals, halogens, you know, they share similar sort of properties. And same thing with our transition metals as you kind of go below on transition metals in sort of a group. They also do share some similar sort of properties, especially around electron configuration. There's a lot of exceptions to kind of the normal electron configuration, and they do share very similar sort of properties in that. Also, as you kind of go across a period on the transition metals, they also have some similar sort of properties within there as well. Now, one thing that we know about transition metals, even from naming right, is that transition metals are typically those guys that can have a variety of sort of charges. And that you might remember from nomenclature. They are sometimes referred to as type 2 compounds when they make ionic compounds. Maybe I learned it as type 2. And that metal means that it can have a variable charge. And that is why we usually will do like Roman numerals when we name these guys. Like iron, Roman numeral 2, iron, Roman numeral 3, because it can have a variety of charges. We do include the Roman numeral there to indicate the charge on it. For the most part, most transition metals will be able to make that variety of charges. There actually are kind of 3 inside the transition metal region that you might also be familiar with that actually, even though they are transition metals, pretty much have a fixed charge, and that is your zinc, that is your cadmium, and you hang a left over there to silver. So even though these guys are transition metals, zinc and cadmium pretty much always make a +2 charge, sort of a fixed charge. Silver pretty much making a +1 charge in terms of constant. But pretty much everybody else in that transition metal region, even as you probably learned as well, a little bit outside of that transition metal region, like lead and tin and so forth, they have a variety of charge or variable charges, which is why we do use, obviously, Roman numerals when we typically name them. In addition, things that are transition metals that have a relatively good positive charge oftentimes will form complex ions. Complex ions are basically a positively charged transition metal, for example, or metal. And attached to that is a number of what are referred to as ligands. Ligands are something that we learned about earlier on in the semester, and they are really what are known as Lewis bases, which we will see a little bit later. And hopefully you remember a Lewis base is something that will basically donate a pair of electrons. So electron pair donor. So give away a pair of electrons. Those are Lewis bases. Remember, Lewis acids are things that are typically electron deficient. that have kind of a positive charge is typically, what we're looking at in that case. Here's a picture of a complex ion, and this is sort of what we see. We see the cobalt kind of in the middle, which is our transition metal. Each of these NH3s are what are referred to as ligands. Why is NH3 a good ligand? Well, if you draw the Lewis structure for NH3, looks a little something like this. It is a polar molecule, and it also has these non-bonding electrons or lone pairs that it's able to donate. And that's, things that are kind of good Lewis bases and that make good ligands, as we'll see more in this chapter, are things that, are either negatively charged, so that implies that they gain some electrons, or things that are polar that have some non-bonding electrons there. And those are things that really do make pretty good ligands. Water is another example of something that's actually a pretty good ligand. Again, is polar, it's got those lone pairs, something like Cl minus, for example. In order for it to become minus, it had to gain some electrons, so it has that sort of separation of charge. Now, when we write the formula for this complex ion, this is sort of what it looks like. And as we finish up this chapter later on, you will eventually know how to properly name that guy. So you no longer have to name it like most people do, that thing, which is a very common one. People always go, not so much because you guys aren't physically doing experiments, but when you do physical experiments, in the instructions, they come across complex ion formulas like that and go, that thing. So you'll actually know how to name that thing a little bit later on in this chapter. And the nice thing about that is, I guess the bad thing about that is this naming. It actually usually will involve a very, very long name these guys have. So sometimes they have very, very long names. Why does this whole complex ion have a +3 charge? Well, it has a +3 charge because NH3 is neutral, has no charge, which means the +3 charge is really coming from the cobalt there. And that's why the overall complex ion there has a +3 charge. Any questions on that there? Now, ionic compounds with transition metals, most of these compounds do make some type of solution that has some different colors. So what I mean by that is, you can actually have the same sort of transition metal involved. And depending on the charge of the transition metal, depending actually on the ligand that's there as well, or how many of those ligands are there, you actually will see some different color of solution. So the same sort of element, if you will, for example, cobalt can make a solution that's more pink in color and one that is more sort of blue in color. Remember that when we see the color of a solution, as we talked about earlier on in lab this semester, what we're actually seeing is the complementary color, right, to the light that's being absorbed, right? So if you remember, I think earlier on we did like the iron sort of solution. It was like a red color, but we didn't really set the spectrometer to red. We set it to the complementary color of red, that greenish sort of area, bluish area. And that's because, again, when we kind of look at a solution, and a lot of transition metals with these ligands attached, do give some different colors of solutions. What we're actually seeing, again, is that sort of complementary color to the colors being absorbed. Many compounds are paramagnetic. What does paramagnetic mean? You might also remember that from maybe electron configuration and stuff like that. Paramagnetic means kind of like unpaired electrons, right? So the more sort of unpaired electrons that you have, sometimes referred to as paramagnetic electrons, right? And orbitals have spin, right? Like the spin quantum number plus a half minus a half. And again, they're affected by each other as they go in to each of those orbitals. And they can actually only go in, right, in a certain sort of way when we do that. So when we talk about electron configuration, just to remind everybody, again, making sure everybody's on the same page, there is an order as to how we do electron configuration. And it's something that you can recreate very quickly. You probably learned this, I imagine, but just in case, I guess you didn't. On the first energy level, s orbitals is where those appear, and they're on every single energy level after that. It's not until the second energy level that we start to see p orbitals appear, and they also sort of find themselves there on some of the rest of the orbitals or energy levels. You might also remember it's not until the third energy level, right, that the d orbitals really start to appear, and that's 4d, that's 5d. And 6d, and not to the fourth energy level that the f orbitals basically appear. We talked about it just a minute ago. The maximum number of electrons in an s orbital is 2 electrons. Maximum number of electrons in a p subshell or sublevel is 6. D subshells, there's 5 of them. That means 10 electrons you could put in there. F subshell, there's 7 of them, which means you could put 14 electrons there in the subshell. Again, remember, each individual orbital can only hold a maximum of 2 electrons. And again, there's 3 different types of p orbitals, right? Px, py, and pz, 5 different types of d orbitals, and 7 different types of f orbitals. So if you know that, and obviously you know what I drew on there on the left there, you don't have to rely on counting it off on the periodic table and making a mistake. You always start at the top and just kind of zigzag back and forth in terms of electron configuration. Major difference, right, in electron configuration, kind of happens right about here. We go 3p to 4s and back to 3d. Remember, in terms of filling order, we do fill the s orbitals first and then the d orbitals as we go through it. So if we looked at something like number 23 here, this is noble gas configuration, which is argon, and 4s2 3d3 would be the configuration. There are a couple of exceptions, or a number of exceptions actually, in the transition metal region. 2 very common exceptions to electron configuration, probably ones that you learned, was chromium and copper. Chromium has 24 electrons, chromium. And again, if you follow sort of the zigzag guy there, 1s2, 2s2, 2p6, 3s2, 3p6, you would do 4s2 and 3d4. And the exception is found experimentally. That's something like chromium. It's actually more stable with an extra electron up there in the d orbital versus the s orbital. And by the way, just a reminder that up to here, if you look at it, that is 10, 18 electrons. That is basically what the argon core configuration basically means. And because we have that extra electron up there in the d orbital, we're basically filling up that d orbital with 1 electron each, and a 4s1 and a 3d5. Copper has a similar sort of exception. Same thing's happening here. We got that extra electron up in the d orbital, 1 less in the sort of s orbital. Now, you might be wondering, how can that sort of happen? So there's a couple of things just to remind you in terms of electrons and transition metals. When electrons go into the atom, the 4s orbital and the 3d orbitals are very, very close in energy to begin with. So it doesn't take a lot, for example, take a lot for this electron to actually make it up to the 3d set of orbitals there, because they're very, very close in energy. In addition, you might also remember this from electron configuration in last semester, that once you start filling the d orbitals with electrons, there's actually a switch in energy that actually occurs between these orbitals. And what ends up happening is the 4s orbital actually becomes higher in energy than the d orbital. And that is why when transition metals lose electrons, they do lose electrons in the s orbitals first. So when they actually start losing electrons, our transition metals, we actually do lose these guys first. These are lost first. And then if you need more electrons, then you delve down into the d orbitals. This is also why sometimes people will write electron configuration not necessarily correctly. They'll write it, kind of in order. Like they'll go, hey, 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2, which in most cases is incorrect. It is correct in the sense of energy. So sometimes you will see people sometimes write it like that. And you shouldn't do that in this class and probably most chemistry classes that you take, because most chemistry classes that you take do it based off of this order here, which is what is referred to as the filling order, not based off of energy. I've only taken one class in my whole life where we wrote it this way, and it was more of a advanced type class because they were talking about energy. But you really probably shouldn't write electron configuration like that. It'll probably be marked wrong in most cases. Most people, when you write electron configuration, write it based on filling rather than energy, and that is really the proper way. There is really this switch in terms of those orbitals that occur, and that's really why when we talk about transition metals losing electrons, they actually do always lose those s's first. Remember that when we look at sort of the periodic table, we have our kind of 4s or 5s or 6s and so forth. And remember, our transition metals start at 3d, 4d, and 5d and so forth. So when these transition metals lose electrons, again, they always sort of pick off those s's first and then dip into those d orbitals. Now, in terms of some exceptions to electron configuration, most of the time, most people in chemistry learn about chromium and copper. You might also learn, for example, silver, and a lot of the guys that are underneath these guys on the periodic table, and even over in the middle between them, there's a lot of exceptions to the normal electron configuration. And you might have learned some of those, for example, like palladium, I think. Doesn't even have any electrons in its s orbitals. They've all been sort of promoted to the d orbitals. So there's a number of common sort of exceptions to electron configuration actually fall below those two guys on the periodic table. And that brings us back to what we were talking earlier, that some of these transition metals that are in the same sort of group or period, they do share similar properties. And again, that is something that is very similar as well. We do see those exceptions to the normal electron configuration happening. Sort of jumped on this a little bit earlier just a second ago, but again, because of that switch in energy that occurs between the 4s and the 3d orbitals, what ends up happening, as I mentioned before, is those 4s orbitals and electrons end up being higher in energy. So when something like Ti, for example, becomes Ti3 plus, if we kind of fill in what we had going on here in terms of electrons, the first thing that's going to happen when it becomes +3 is it means that it lost 3 electrons, and those electrons that really will be sort of taken out to lose are first going to be those two. So those are 2 electrons that are gone. It needs to lose 1 more. It's going to take out 1 more there. And as you can see, that will leave you just 1 3D electron left at that point for the electron configuration. So unlike sort of representative elements where when things lose electrons, we just simply take it off the last sort of guys in the electron configuration, is not such the same effect happening here when we're dealing with transition metals. Any questions on that there? All right, so why don't you write the electron configuration for nickel with a +4 charge, and why not? Why don't we also do iron with a +3 charge? In case you don't have your periodic table, iron is number 26 atomic number, and nickel is 28. So take a second, write the correct electron configuration for these transition metal ions of what it should be. Okay, let's take a look. Well, let's take a look first off at just the electron configuration of each of these without no charge, or with no charge. That's a better way of saying that. So if we did 28, the long way, 1s2, 2s2, 2p6, 3s2, 3p6, a little 4s2 action there, and 3d8 sounds like a winner, I hope. So this would be nickel. If we were going to do nickel with a +4 charge, that means that it basically has lost 4 electrons. Again, the 4 electrons it's going to lose is it's going to lose our s electrons first. So those guys go away. That is 2 electrons. We then need to go into our next highest electrons, which would be there, and dig out 2, leaving us a 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 at that point. Or, of course, you could do argon 3d6 if you like. Question on that particular one there. So again, a little bit different, not the last thing written in the configuration. If we do the same thing for iron, is 26, so pretty close there. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d should be 6, I believe. 2, 4, 6. Same thing here. I +3 indicates as it went from there to there, we lost 3 electrons. That means we need to take, again, our S's out first because it's a transition metal. We still need 1 more electron to come out. Again, this first part here is argon, and we would be left with 3d5 at that point. Any questions on how to write electron configuration for transition metals?
Professor?
Yeah.
For nickel 4 plus, why is it not 4s1 3d5? Isn't that more stable?
For which one? I'm sorry, nickel.
Nickel 4 plus, yeah.
Nickel 4 plus. No, so the 4s electrons would be lost first, so they're gone because they're highest in energy. So in terms of the nickel, just looking at the end part of it, basically these 2 electrons, and we got these guys, and we got 8 of those. So 1, 2, 3, 4, 5, 6, 7, and 8. So when it goes and loses those 4 electrons, it's really going to plop off the highest ones first. Because of that switch in energy, these 2 are for sure will go first. And then it will dig in and, take out the next 2 highest ones out of there, leaving us our 6 electrons that are left at that point. So the 2 exceptions in that first row transition metal is really only chromium and copper. These are the only 2 that have that sort of 4s1, 3d5 ending, or 4s1, 3d10 ending. Now, for example, if copper lost an electron and became copper +1, it would lose this guy first, and it would end up as argon 3d10, basically. Again, that orbital, that 4s orbital, again, they're really close in energy to begin with when they come in, the electrons, but there is that switch that occurs when we start putting those d orbitals, our electrons in those d orbitals. So the 4s actually ends up being higher. And always when things sort of lose their electrons, they always lose the highest energy level ones first. And then, if they still need to lose more, which really only happens sort of in the transition metal region, then they go to the next highest and stuff like that. In terms of representative metals, they always lose those last valence electrons and move them back to a noble gas. Doesn't necessarily happen with our transition metals. They don't necessarily end up at noble gas configuration like representative elements. Other questions? Okay, so obviously transition metals, you need to know some stuff about them. You need to be able to write electron configuration correctly with charges, without charges, and stuff like that. So let's just finish up here talking about some important trends that we see sort of on the periodic table and with transition metals as well. And again, some of these things hopefully should be a little bit of a review for you. And you usually cover it, a little bit as you go through 1A. Let's talk about oxidation states. So obviously, transition metals can have a variety of sort of oxidation states or charges, if you will. A lot of times they do have common charges, our most commonly found charges, which again, I'm not sure how it shows up on the screen, but kind of the red ones here are the kind of most stable or common sort of oxidation numbers that we see for things. And what you see is a lot of those transition metals, and this is looking at the first period or the first row transition metals, a lot of them are +2s, +3s. We do see sort of an increase, if you will, in sort of the common oxidation number as we head to the center there where Mn is, and then we kind of come back down on the backside. You can see Mn, it has a ton of different oxidation states, as we talked about, I think, with oxidation numbers. A reminder that, it's not necessarily perhaps the charge we normally associate with things sometimes, especially when we're dealing with nonmetals, but it is sort of the charge it has in that sort of orientation it's in that compound. But most transition metals, or a lot of transition metals, have commonly +2, +3 type charges, but you can see they can get very large, like Mn. Manganese has a number of those guys in terms of those transition or those oxidation states. Another important trend is ionization energy, and you might remember maybe what ionization energy is. Ionization energy is the minimum amount of energy that's required basically to remove an electron from the gas phase. So when we remove electrons, right, things become positively charged. So a lot of times we associate ionization energy with the formation of cations, right? That's pretty much what happens when we kind of remove electrons. And you might also remember that electrons, they actually do come off one at a time. And what I mean by that is, for example, magnesium will not drop both electrons at once. It actually comes off in a stepwise fashion, almost like how hydrogens come off when we talk about acids and diprotic acids, triprotic acids. It's a stepwise sort of fashion in which electrons are lost. The general trend for ionization energy on the periodic table is as you go to the right, it increases. As you go down, it decreases. And that makes sense if you think about to the right on the periodic table, those are our nonmetals. Those are guys that typically will accept electrons and gain electrons. So it takes a lot of energy to remove an electron. It usually doesn't happen. And as you go to the left and down on the periodic table, right, that's where all of our metals are. And those typically are the guys that will let go of electrons and give up electrons. So they have very small ionization energy. It doesn't take a lot to sort of convince them to basically lose electrons. When you look at ionization energy tables such as this, you'll see like this is ionization energy 1, second ionization energy, third ionization energy, fourth ionization energy, and so forth. What do those numbers represent? Those numbers represent the energy required basically to remove each of those electrons, basically one at a time. So if we look at something like sodium, right? Sodium decides it's going to drop off an electron. That is what is known as the first ionization energy to do that. If we look at that table, it's something like 495 kilojoules, I think it is on that table. Now, the next thing that would happen would be sodium would then lose a second electron. And that would be the second ionization energy, which if we look at the table is about 4560 kilojoules. what just happened here as we went from the first electron to the second electron? Well, if we look at the electron configuration for sodium here, it is 1s2, 2s2, 2p6, 3s1. Yeah. If we think about our core electrons, that's these guys right here, right? These are our core electrons. This is our valence electron, right? Sodium's group 1, it has 1 valence electron. So what happens is sodium is more than happy to give up that first electron. You know, it only takes about 495 kilojoules to do that, to become positively one charge. The problem that occurs is when it gives up that electron, what's going to happen to the sodium ion? It is going to get larger or smaller. Hopefully, you know, it should get smaller, right? It lost some electrons, overall electron cloud shrinks. The further electrons are now even closer in, which means that these electrons here, these nice core electrons, with the loss of that electron, that first electron is now going to be closer to the nucleus because you now have more protons than electrons. Going to pull everybody in. And now you're going to try to rip off for that second electron one of those core electrons. And it's not going to happen because you need almost like, what is that, like 10 times the energy to do that. Is not going to happen because we have now delved into our core electrons at this point. So that's why when we look at something like sodium, it really will only lose one electron because after that, everything gets really compact. Those electrons are held a lot tighter. It takes a tremendously way more energy to try to remove that core electron. It doesn't typically happen. If we look at something like magnesium, which is group 2 on the periodic table, and magnesium, the first thing that would happen is it would lay up an electron. That's going to be its first ionization energy. Next thing, which by the way, we'll go to the table, that's 735. Next thing that will happen is that magnesium with +1 charge will then lay up another electron. That's going to be a second ionization energy, 1445. Then if we go one more, test our luck here, get some magnesium with a +3 charge and another electron, that would be the third ionization energy, which according to this table is 77.3. So let's take a look at what's happening here. Again, if we look at the electron configuration for magnesium, it is neon 3s2. That would be the valence electrons. And here would be 1s2, 2s2, 2p6, which would be our core electrons. Now, when we lose that first electron, not a problem, not a big situation. We're going to lose it. It does take a little bit more energy, right? And we can see compared to sodium, which is right next to it, it takes some more energy to do that. And that makes sense because we're going in this direction. Now, when we lose the second one, okay, it's going to happen. We've now almost doubled, right, the amount of energy to do that. Why is it harder to take that one off? Well, again, the same thing's happening when we lose that first electron, that second valence electron, and everybody else is now just moved closer to the nucleus because the nucleus now has more protons than electrons, going to draw everybody in, going to mean that that second electron here is going to be held tighter, going to take more energy to drop off that second electron. Once we get rid of that second electron, we're going to collapse even more, if you will. It's going to bring those electrons in tighter. And now that we got rid of these two, we're left with our core electrons. Again, a tremendous jump now, a almost 7 times jump there in energy to try to remove that third electron, which doesn't happen for magnesium, again, because we have now crossed over into our core electrons. So what we see with ionization energy is a couple of common trends. We see that it does increase, obviously, like we see between sodium and magnesium. It increases as you go to the right on the periodic table. We also see that as you go from the first ionization energy, removing the first electron, to the second one, removing the second one, to maybe the third one, removing the third one, the ionization energy increases as you go from first to second to third. And again, the idea there is as you remove the electrons, everybody gets closer to the nucleus, closer to that positive charge, held a lot tighter. And definitely once you get to those core electrons, which as we talked about earlier, feels really the full brunt of that positive charge, it gets tremendously hard and almost impossible to remove that electron at that point. And that's sort of the general trend that we see in terms of ionization energy. The first ionization energy is always lower than the second. Second is higher than obviously the first and the third and so forth. Any questions about ionization energy? So let's take a look at a few other sort of trends. Obviously, you should memorize every number on this table. I'm kidding. Don't do that. That is a waste of time. But some general trends we talked about, again, as we go across the period there in the first row, transition metals, we get smaller in terms of the atomic radius. We also talked about here +3, +2, very common sort of oxidation states that we see. In general, we got sort of a trend in density that's sort of increasing as we go from left to right in terms of the periodic table. Some other trends here, the blue dots is our third ionization energy, the kind of red dots are our first. And as we were just talking about, as you keep pulling off those electrons from an element, it gets harder and harder to pull off because everybody gets closer, held tighter, takes a lot more energy to do that. And that's what we see here. The blue dots, which is like the third electron coming off, much higher than obviously the red dots, which is the first electron that comes off. Here's another graph in case you hated the first two, and showing our second one in there as well. But we see that general trend of first is lower ionization energy than the second, second is lower than third, and so forth. And also sort of a rise in ionization energy as you go from left to right across that period. Another kind of important trend was referred to as electron affinity. Electron affinity is not electronegativity. So again, electronegativity is different. Electronegativity is probably what you talked about when you talked about bonding. That increases as you go to the right, decreases as you go down. Electronegativity is the ability of an atom to attract electrons, right? Electron affinity is the energy change that occurs when an electron is accepted by an atom. So when we talk about just a second ago, ionization energy is kind of referring to cations being formed. Electron affinity is kind of what happens in terms of energy when anions are formed. They become more negative because they're gaining electrons, and it's the energy change that actually occurs. The general trend is kind of similar to electronegativity as well, but it decreases as you go down on the periodic table, increases as you go up. It's not perfect. So this is group 7 on the periodic table. And obviously going up on the periodic table, we see an increase in the electron affinity in terms of the change in energy that's occurring. It's not perfect. Obviously here, fluorine is less than chlorine, but the general trend for electron affinity is sort of increasing up to the right on the periodic table, decreasing down. And again, this is more the energy change that occurs when an atom gains that electron. Kind of the larger negative part, the more electron affinity it is. Affinity usually means that you like something, right? So things going up and to the right on the periodic tables are nonmetals. Also makes sense that they would like electrons and have a higher electron affinity. There's another table similar to the one we just saw earlier. This is a relative reducing abilities of the first row transition metals. And we see a couple of things here. We see that the reducing ability increases as we go to the left. on the periodic table. Also really important when you look at this reaction here, you might be thinking this looks just like my SRP type of table that I saw earlier in the previous chapter, and you would be kind of incorrect. These reactions here, these are all oxidation reactions. Why are they oxidation reactions? We see electrons on the product side. These are not really standard reduction potential. Sometimes people call it standard oxidation potential. And that is why we see kind of an opposite trend here. Reducing ability coming up means that the guy going to the top is most likely going to be oxidized. While this guy down here is most likely going to be reduced. And you may be saying to yourself, wait, that's more positive, right? And again, we're not looking at standard reduction potential here in this table. We're looking at oxidation potential. What would happen if I reverse each of these reactions and turn them into a standard reduction potential? That means that the sign of each of these guys change. So if I turn this guy into a reduction reaction, like SC3 plus 3 electrons go to this, it would be negative 2.08. The next guy would be negative, 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 all the way down until my copper, which if I flipped it around, would end up being positive 0.34 volts. And what we know about the thing being more positive is it is most likely going to be reduced, right? Guy that's more negative will be most likely be oxidized. So it is actually telling you the same thing, but you do have to watch out for things. Again, although it may look like an SRP table, it's actually the opposite. And that's why, again, it may think it's giving you opposite information, but it's actually not. It's the same information that you would get from an SRP table. Any questions on that there? All right. And we talked about this as well. Again, really because of all these properties, what we generally see as we go from left to right on the periodic table in terms of size is we do see sort of a decrease in the size or of the atom, especially the transition metal. And again, really, it's sort of the idea of that build-up principle. As you go to the right on the periodic table, you're building up more and more protons. More and more protons is going to give even those outer electrons a greater effective nuclear charge, going to bring them in tighter and also make the size of the atoms smaller. In case you've never seen the first row transition metals, these are examples of what they look like. And any questions on that there? And by the way, they make a lot of different sort of ions, and you can see, for example, here, these are some different colors of solutions with chromium. We got some green, some blue, some oranges. We got some MNs, which are pink, brown, purple, iron as well. You can see has a little bit different colors that are in there, cobalt happening, and nickel. So as we talked about earlier, depending on the charge of that transition metal, you will get some different colors of solutions, maybe even solids that are made as well, depending on that. Any questions on transition metals, general trends? So you need to know, like I said before, a little bit about transition metals, how to write electron configuration for transition metals. You should know where they're located, I would hope. You should know some of these general trends that we talked about the periodic table here in regards to transition metals and just in general, ionization energy, electron affinity, and stuff like that. Any questions on any of that stuff? All right, sounds good. Have a nice weekend. Yes, we